Okay, so there were six past and present long baseline experiments, and I've grouped them into three different classes. There were the first generation experiments that I'll talk about, K2K and MINOS. There were second generation experiments, which are still going on, T2K and NOVA. And then, for lack of a better name, we'll call specialized experiments, OPERA and Icarus. Now, since studying oscillations can be the only conceivable reason why you might want to put your detector hundreds of kilometers from your target, that's the only subject I'll cover here, though these experiments all investigated other things than the oscillations. And since I've only been allotted an average of 4 minutes and 10 seconds per experiment, with one exception, I will not discuss sterile neutrino searches. Let me just say that at present, none of these experiments have found any evidence for sterile neutrinos. So the first generation of experiments was motivated by, of course, these atmospheric results that we've already talked about, and particularly since they started around 1994 by the Kamiokande result, which is shown right here. And what you'll notice is that this result had a big delta M squared value, which is about an order of magnitude too high. And this will have consequences. Measurements have consequences. This will have consequences for the planning of these long baseline experiments, which I'll discuss. In 1998, of course, Super Kamiokande came, and still a little high in their initial measurements, but definitely lower than Kamiokande. And of course, there was still a confusion in people's minds over which of these was correct. Now, the KEK experiment used the KEK Lab's 12 GeV synchrotron at Tsukuba to send about a 1.4 GeV neutrino beam 250 kilometers to the 50 kiloton Super Kamiokande detector. Oh, by the way, I have numerous references at the end of the talk, which you can look at your leisure, which will be indicated here. Now, in common with all of the accelerator-produced neutrino beams, the KEK neutrino beam was composed of approximately 99% nu mu, 1% nu e from kaon and muon decays. And thus, the attempted measurements in these experiments will be either nu mu CC disappearance or nu E appearance. And in a two neutrino model, what you measure is in the disappearance is 1 minus this sine squared 2 theta times this dynamic term. And in nu E appearance, again, an envelope term times the same, essentially the same dynamic term. Now, let me make a comment on near detectors. All of the experiments, with exception of the ones at Gran Sasso, have used the comparison between a near and a far detector to measure the effects of the oscillations. And this is an essential method of reducing the systematic uncertainties, since the uncertainties basically due to flux, cross-sections, and efficiencies will mostly cancel. Not completely, but mostly. The US experiments, which were all scintillator experiments, both of them were scintillator experiments, use functionally equivalent near detectors. In other words, a near detector was just a small version of the far detector. The Japanese experiments are using water Cherenkov detectors, and they will use either functionally equivalent fine-grained or both, which I'll in fact show you. Now, the use of fine-grained near detectors for water Cherenkov far detectors makes a lot of sense, because the water Cherenkov technique is not sensitive to the whole event, because some of the energy is below threshold. Here is actually, it's a very beautiful near detector by KEK. They start with a functionally equivalent detector with the same phototubes and everything as Super K, and then they add fine-grained elements to it. Now, KEK realized that they would not be competitive in the long run with the Minos detector. Basically, the problem they had was the source of their neutrinos. The synchrotron was too weak. But they could be the first accelerator experiment to confirm the Kamiokande result, and after 1998, resolve the difference between the two delta M squareds. And they ran from June 1999 to November 2004 and accumulated 0.9 times 10 to the 20 protons on target. Now, the first results came in 2002, and the final results were published in 2006. I'll show you them in the next slide. They also searched for new E appearance, but they only found one candidate with an expected background of 1.7. And this allowed them at least to set a limit on this effective envelope function of 0.13, which is about 3 times the current effective value. So here are the plots, and here's their initial one, and you see it's favoring the lower value, but it's still too high. And then finally, here's the comparison. Here's the K to K result. I'm sorry. Here's the green is the K to K result. Here's the Super Kamiokande result. They're quite consistent. KEK is not quite as good as Super Kamiokande, but they're both getting this lower range. But this is already 2006. Now, let me move to the Minos experiment. The first proposal for a long baseline neutrino oscillation at Fermilab came in 1991, and it was updated in 1993. And this was a proposal from the Sudan collaboration, and they proposed a beam to their 1 kiloton finely segmented iron calorimeter in the Sudan mine in northern Minnesota, which had been studying atmospheric neutrinos and searching for proton decay. The program advisory committee at Fermilab felt that a 1 kiloton detector was just too small, and they called for more ambitious expressions of interest in 1994. And it turns out 3 of these were received, one from the Sudan group, one from US groups working on the macro experiment, and one was a one-person expression of interest from Stan Wojcicki, who was proposing sending the beam to SLAC. Now, the POC asked the 3 groups to get together and submit a single proposal, and they did that in 1995, choosing Stan as the spokesperson for the experiment. The proposal called for a 10 kiloton toroidally magnetized iron plastic limited streamer tube sandwich detector with 4 centimeter thick iron plates and 1 centimeter tubes. What was actually built was a 5.4 kiloton detector. This is going to be a repeating story. With basically 1 inch thick iron plates and 4 centimeter wide plastic scintillator strips. The far site was chosen to be the Sudan mine, which gave a 735 kilometer baseline. Now, the rationale for this choice was that the Sudan detector was already there. So if they built the beam before the Minos detector was built, they'd have a detector there to start working with. The irony of the situation was the Minos detector was completed 2 years before the beam was ready. The fly in the ointment here was that there was a competing proposal from Brookhaven National Lab in 1994 for a long baseline experiment that had 4 identical 4.5 kiloton water Cherenkov detectors located at 1, 3, 24, and 68 kilometers from the target, and they were off-axis. They were 1.5 degrees to the neutrino beam, and I think this is the first example of a off-axis experiment. Now, I'll talk about this later. The off-axis configuration produces a narrowband beam. Sasha already referred to this, focused ideally on the oscillation maximum, a scheme that would later be adopted by both T-Decay and the NOVA experiments. However, you note that if you're going to focus the beam, it would be useful to know where to focus it. And unfortunately, this proposal was using the Kamiokande measurement of delta M squared, which would have focused a beam an order of magnitude too high in L over E. In any case, to settle this, the High Energy Physics Advisory Panel, HEPAP, requested a sub-panel, which was chaired by Frank Scully, to make recommendations on neutrino oscillation experiments. And in September 1995, this sub-panel unanimously recommended that MINOS be supported and the Brookhaven experiment not be supported. And the three reasons they gave were, MINOS had better sensitivity to low values of delta M squared, which was still in doubt what the right value was. And this turned out to be, in fact, the crucial right decision. Also, MINOS had better exploration capabilities, and the third thing was that it could use the same baseline as an already approved short baseline experiment, Cosmos, and it was clearly more cost-effective to have one neutrino beam than two. This last result turned out to be irrelevant because Cosmos was never funded. Now, MINOS took data from February 2006 to April 2012 and accumulated 10.7 10 to the 20 protons on target in the neutrino mode and 3.4 10 to the 20 in the anti-neutrino mode. The first publication was in 2006, and the final results were reported in 2014. And I'll show you basically what happened here is that MINOS could do a good job on the with a magnetized detector on the nu mu disappearance. On the other hand, a detector with 1.4 radiation length iron plates was not optimum for measuring nu E appearance, where you have to distinguish the nu E events from the neutral current events. Nonetheless, his heroic effort was made to pull out a signal which came out about 1.8 sigma. They had 152 candidate electron neutrino events with an expected neutral current dominated background of 128. In anti-neutrino mode, the 20 candidates with an expected background of 17.5. Now, let me make a comment. One of the aspects of the NUMI beam was that you could tune the energy ideally by changing both the target location and the second horn location, but in fact, it was sufficient to just move the target. We had a movable target, and you could get anything. These are just three examples: a low energy beam, a medium energy beam, or a high energy beam. And for MINOS, the low energy beam was the most useful because the oscillation's down here. It's really down at the edge even of the low energy beam. This is a consequence, again, of the Kamiokande result. The NUMI beam was not optimized for the lowest energies. It had a long, thin beam pipe. It should have had a short, fat beam pipe. This was only realized quite a bit later. But when NOVA started running, it used the medium energy beam because it was using an off-axis technique. And so what happened is MINOS decided to keep running. They reorganized as MINOS Plus. They were now pretty insensitive to the oscillation region down here. But the main goal was searching for non-standard interactions in sterile neutrinos. And they did that, and they ended their data taking actually in June 2016. Now I turn to the CNGS, and this is going to be some related comments to what Alain made yesterday. In 1999, CERN committed itself to a program of new tau appearance experiments. And the question I want to sort of leave for the discussion is why? It was obvious to me at the time, and to many other people, of course, that this program would not be competitive with what we would learn better from other measurements in a comparable time period. And the argument is actually quite simple. We know from LEP that there are only 3 active neutrino species. We know from Super K that nu E appearance was small, and this left only tau neutrinos and sterile neutrinos. And MINOS would search for sterile neutrinos with higher precision by searching for neutral current disappearance, which in fact they did, and didn't find anything. So here's my list of possible reasons why CERN went in this direction. One was the absence of a near detector. Now, the reason for that, presumably, was that the only possible place to put that detector was underneath the Geneva airport, which was probably impractical. There is an official CERN document I found that claims that a near detector is not needed for an appearance experiment. This generic statement is not true. But in this case it was, because the statistical uncertainties would be large enough that the systematics wouldn't matter. Now, the second was a desire to do something different from Japan and the United States, the interest of Italian and other physicists in pursuing the emulsion technology, pressure from Italy to enhance the Gran Sasso program, and I note that that Italy was committed, Italian sources were committed to providing 68% of the marginal cost of this beam. And the possible last one was a conviction that nu tau appearance is a crucial measurement. So the OPERA experiment was composed, it's actually a beautiful experiment. It was composed of 1.1 1/4 kilotons of sandwiches of 1 millimeter lead plates and emulsion films. And the idea was to identify nu taus by observing kinks in their decay from the emulsion films. Scintillator trackers located the location of the events in these, what they call lead emulsion bricks, which they could then remove for analysis once they had a trigger. Experiment was located 730 kilometers from CERN in the SPS neutrino beam target, from the target, and it ran from 2008 to 2012, accumulating 1.8 10 to the 20 protons on target. Now, in order to optimize for nu tau appearance, the neutrino beam was tuned to an average energy of about 17 GeV. And for observing nu tau appearance, that's actually approximately where you should be. But the problem is that this yielded an L over E more than an order of magnitude smaller than the oscillation maximum. And the rate goes as the square of that. So they had resulting in more than 2 orders of magnitude suppression from this dynamic term. So this, of course, leads to low statistics, which they anticipated from the start. They reported their first event in 2010. They had a total of 5 events by 2015 when they presented their presumably final result. But actually this year, there's a new analysis with looser selection criteria, and they now have 10 nu tau candidates were found with an expected background of 2 and an expected signal of 6.8. I'll move to the Icarus experiment. This has a long history. It starts actually in 1977 when Carlo Rubbia proposed using a liquid argon TPC as a neutrino detector. And research started at CERN in 1985 on 2 cubic meter prototype and continued in 1993 in Pavia with a 10 cubic meter prototype. And finally, with 2 300-ton modules, one of which successfully took cosmic data for about 100 days in 2001 in Pavia. The 600-ton detector was then transported to the Gran Sasso in 2004 and ran for a couple of years, 2010 to 2012, in the beam. Now, the problem that Icarus had was that it always had considered this 600 tons to be just the first part of a multi-kiloton detector. Their proposals were always somewhere between 3 and 5 kilotons. But the additional modules were not funded. The reason supposedly was that it was felt that their modular technique was not scalable. The combination of the same L/E factor of over 100 that affected Opera, of course, affected them, and the relatively small mass of the detector really prevented them from doing any oscillation physics at the atmospheric mass scale. The only oscillation result from Icarus, in fact, was a limit on sterile neutrinos at looking for sterile neutrinos of higher mass where the L/E was not so severe. And they have, it's actually not that good a limit, but here's their compared to other people's limits, but there's their limit on sterile neutrinos. Okay, now we'll move on to the second generation experiments, T decay and NOVA. Now these two experiments are complementary experiments with similar capabilities and interest. The major difference is the longer baseline of the NOVA experiment, and this will be important in measuring the mass ordering of the neutrinos, because that measurement comes from a coherent forward scattering of the electron neutrinos off the electrons in the Earth, which is coherent over the entire length. And so the longer the length you have, the more coherence you have. And it gives basically, I don't have it written down here, but NOVA plus or minus 30% enhancement or suppression, whereas T decay only has about a 10%. And I'll show you later a plot that illustrates that. Now, both place the detectors off the beam axis to increase this, the neutrino flux near the oscillation maximum and reduce backgrounds from higher energy neutral currents. The higher energy neutral currents, of course, won't have all of the energy, so they'll look to the detector like lower energy experiments. And Sasha's already discussed why this happens. Here's a picture of both what happens at T decay and NOVA. NOVA is the more dramatic case. Here's the medium energy beam. It's run at 0 degrees. And here's the resulting off-axis beam at 14 milliradians. You can see you have much more flux and much less background from the higher energy events. Now, both T decay and NOVA use the same, at present, use the same idea. You take 3 measurements, the solar measurements and the theta 1,3 measurement from reactors from those experiments, and you combine that with the measurements of T decay and or NOVA to do nu mu disappearance and nu E appearance in both neutrino and antineutrino beams, and that gives you information on the other 4 parameters of the standard neutrino model, which is the magnitude of the mass squared, delta m squared, this mixing angle sine squared theta 2,3, and these are best measured in the nu mu disappearance experiment, and the CP violating phase, and the mass ordering, which is best measured in the nu E appearance. There's a bit of a kicker here which complicates things. What we actually measure is sine squared 2 theta 2,3, as you can see from this formula. But what we want to know is sine squared theta 2,3, because that's a term that modifies the atmospheric part of the nu E appearance. And so you measure something where the derivative is close to 0, and from that you derive something which is now double valued because you can't tell whether it was greater than or less than pi over 4. And it's where the derivative is high. So it's a very difficult measurement. A precise measurement here leads to still considerable errors there. The T to K experiment, of course, uses, I'm going to switch to my own pointer because this one's dying, uses Super Kamiokande detector as K2K did. However, the neutrino beam is now generated by the more powerful 30 GeV J-Park proton synchrotron in Tokai, and that gives you a slightly longer baseline of 295 kilometers. The near detector is a rather sophisticated device. It involves sandwiches of a pi naught detector consisting sandwiches of scintillators, water bags, and either brass or lead sheets, followed by TPCs and fine-grained scintillator bars, all included in a 200 Gauss magnetic field. Now the timetable for T to K is they submitted a letter of intent in 2001. The experiment was approved in 2003, and the beamline construction started around 2004. The first run with beam was in January 2010, and the first publication on oscillations came in 2011. Now, they did have some unfortunate incidents that slowed them down. One was a tsunami in 2011. And the second was a radiation incident at the lab, which had nothing to do with them, but it shut the whole lab down. And that happened in 2013. So their most recent report, so basically I'll show you, in fact, a summary of all of these at the end. Their most recent report has 14.9 10 to the 20 protons on target in neutrinos, and 11.2 10 to the 20 in antineutrinos. I've chosen two benchmarks to compare all these experiments. One is the delta M squared precision, and they have the best on that. It's plus or minus 2.6%. And the new E signal, where the figure of merit is the signal over the square root of the signal plus background, so sort of a significance, except that it's only done with the statistics. And they have reported 75.2 signal events on 14.8 background events for a figure of merit of 7.9. And in the antineutrinos, they have 4.7 events on a background of on top of a background of 4.3 events for a figure of merit of 2.3. Okay, the NOVA experiment. So the NOVA FAR detector is located in northern Minnesota near the Canadian border at a baseline of 810 kilometers. In fact, the sighting location was as close to the Canadian border as we could get. The only reason we couldn't get slightly closer is there's a national park that comes next. But the 14 kiloton detector consists of about 300,000 of these 15 meter by 4 centimeter by 6 centimeter PVC cells filled with liquid scintillator, read out by a loop of wavelength shifting fiber on both ends connected to an avalanche photodiode. The near detector is identical, except it's much smaller. Now planning, the timeline here is that planning actually started with some workshops around 2002 that led to a proposal submitted to the Fermilab PAC in March of 2005, and it was given preliminary approval at that time. The proposal called for a 30 kiloton version of what was actually built. In other words, what was proposed was built, but not 30 kilotons, as you'll see. At the request of the Department of Energy, the next year, NOVA downsized the mass to 25 kilotons. There was another panel from HEPAP called P5, and in 2006 it recommended the construction of NOVA starting in 2008. So this was all fine except for one thing. In December of 2007, the US Congress cut NOVA funding to zero. Now, this was a little strange because both congressional committees, the Senate and the House of Representatives, were in favor of NOVA, as was the administration. So it's not clear how this happened. But as you may be aware, we don't have a parliamentary form of government in the United States. So we don't have a government in the sense that European countries do. And so lots of the time, nothing gets done until the last possible minute. And then what's called an omnibus funding bill is produced, and it's voted on before anyone has time to actually read it. So it's not clear how this happened. It was probably some 20-year-old staff member that was following some general instructions that had no idea of what neutrinos were. But in any case, this was devastating in the sense that Fermilab employees who were working on NOVA were assigned to other tasks. Now, the funding was restored about 6 months later, but it took time now to get all these people back and rebuild the team and so forth. So we probably lost about a year in this whole process. In May 2009, the NOVA construction began. And what happened here is the Department of Energy fixed the cost at $278 million, and part of that actually was about $80 million was for accelerator improvements. And the DOE instructions were build as much detector as you can for that amount. Since it's a modular detector, you can do that. And the detector, the pit that it was put in, it's basically a surface detector. It has a pit just for containment, was sized at 18 kilotons. But what actually got built, we ran out of money after 14 kilotons. So the first data was taken on actually 4 kilotons of the FAR detector in 2014, and then in February, and then in November, we had the full detector and started taking data in a regular way on the full detector. The first oscillation results were published in 2016, and here's the sort of most recent report from the Neutrino conference this summer. We have 8.8 times 10 to the 20 protons on target in neutrinos, 6.9 10 to the 20 in antineutrinos, a delta M squared precision of 4%, 43 signal events on top of a background of 15 for a foam of 5.6, 12.7 signal antineutrino events on top of a background of 5.3 for a figure of merit of 3. So slightly worse, somewhat worse than T to K in neutrinos, somewhat better in antineutrinos. So let me, these are plots of the number of nu E versus the number of nu E bar candidates. And they don't represent the entire analysis, such as the energy dependencies, but they're good pedagogical tools for showing the whole multivariable landscape. So here, for instance, is the one for NOVA, and what you see is, here's the data, number of neutrino events along the horizontal axis, number of antineutrino events, these are nu E appearance, of course, along the vertical axis, and then the physics, except for the delta M squared, is represented by these ellipses. What they represent is the blue ellipses are the normal mass ordering, the red ellipses are the inverted mass ordering. If you go around the ellipse, that's the CP violation from 0 to 2 pi. And along this axis is the sine squared theta 2, 3. And the reason why there's 2 here is because it's double valued, and this was drawn with the 2 best points from NOVA. This is the only thing I could, okay, so this is T to K's version, and I have to say that this is not the current data. This is 2017 data. They reported new data at the Neutrino conference, and in fact, at the Neutrino conference, I requested an updated version of this and was told to be put in the slides. It was not put in the slides, and I could not find the updated version anywhere in T to K talks and so forth. So I would be happy if anyone has a copy of an updated version. I suspect it doesn't exist, but it would be useful to have. So here you see the ellipses. Now these are actually ellipses because we're a little above the oscillation maximum. T to K is right on the maximum, so these become lines instead of ellipses. And here they are. You notice that the blue and red are now heavily overlapping in contrast to this. That's just due to the baseline difference. And here's their data, which is sort of outside the standard model. But in both of these cases, what I really have to emphasize is we're at an early stage. We're at an early stage in the running of these experiments. Both of them will run for at least another 6 years, possibly longer. We have some hopes that we'll start to converge on these parameters. And we're even committed to try to do a joint publication in 2021. Okay, so this is really sort of the end of the talk. I just have some things in the slides that you can look at later if you want. Here's when the running took place for each of these experiments. Here's a summary of how each of these experiments met these 2 benchmarks that I've defined. And I thought, just for fun, I wanted to do some demographics. It's interesting, these are actually circles, but they get distorted. So this shows basically the number of authors. The area shows the number of authors for each of these experiments. I chose typically their final publication or their most recent publication, and which continents the members of the collaboration come from. So it's an interesting demographic study. So I'll finish at this point and open it for discussion.
I had 3 very short remarks to make. One is that in this, over here, Gary, in the corner, is that it's remarkable in the Icarus program that this thing went on for 40 years. And I think for the historians here, that maybe the item to point out is that the only reason that it survived that long was 2 super strong personalities who were able to keep it alive, Carlo Rubbia and Dave Klein, because it dragged on for all these times. Many of us have been fans of that technique over many years, but it's remarkable that it was somehow kept alive long enough and has now been taken up by Dune. A comment about the T to K personnel, the large number of personnel. It's been a great boon to T to K that there was not a hell of a lot going on in the rest of high energy physics at the time that it was formed up. And there were a lot of refugees from CERN and other places where there were not projects that were marching ahead and giving them good topics for theses and so on. And so we had all these refugees from accelerator physics joined T to K, completely overwhelming the Super K crowd. So there have been lots of jokes made about the beam monitor for Super K that has 4 times as many collaborators as the Super K experiment. Another little comment for the historical record, and one that's great to point out to your students, is in the K to K experiment. When we first started running, there was something remarkable that happened. We saw a few events, and then we didn't see any events, and we continued not to see any events, and everyone's getting more and more nervous, and we keep looking every day. Did we get another event? Did we get another event? It got up to, I don't remember, something like 5.2 sigma, and we started resurveying the beam, some people said, well, we had the orientation of Super K wrong, and various things like that. And then finally we began to see events again. But it's a great story about the watched pot, that you have to take account of the number of times that you've sampled. But it got up to discovery level that we were seeing no events, and yet it all blew over in the end. The statistics worked out. End of comment.
Yeah, thanks for those comments. I'll make a couple comments. One is that, of course, the 600-ton Icarus detector has been refurbished and is now, I believe, now at Fermilab to be the FAR detector for the short baseline program. The other is that this 4% right here, that's Dave Klein and one collaborator from UCLA.
Just to play the devil's advocate on opera, the evidence for nu tau oscillation that comes from the neutral currents was never really quantified in terms of significance, or at least I never really can find in my memory when that was quantified significantly as a proper demonstration that the nu mu's oscillate into tau neutrinos. Do you have a particular point in time or reference for that?
Well, no. Let me comment. The interesting thing I found, and I haven't looked back to see what the actual significances are, is that the two experiments were asking different questions. The null hypothesis for opera was there's no tau appearance. The null hypothesis for the neutral current, for instance, Mino's neutral current search, and the other ones, is that there is 100% tau, well, 100% other than the electrons, that all of the excess is going into
active
tau neutrinos. So the two never published the other side of the result.
Right.
In other words, opera never said what kind of a limit they had on sterile neutrinos, and the sterile neutrino search never said how many sigma they had for tau.
Yeah, surely one should be able to reconstruct that, though.
Yeah, we can certainly do it.
So my question is, you see, I'm here, so hello. Hi. Actually, so when not only searching for these events, do you also have to search for young people to join the experiment? Because they take such a long time that you really need to have crown princesses and crown princes who can continue your work, maybe have a future Carlo Rubbia who will excite people and so on.
Well, all of these, yeah, that's a good comment. All of these experiments take a long time.
Yes.
And what I found was that it was hard, that a few years ago it was hard to get students because they all wanted to work on LHC. Now we're finding that working on LHC isn't quite as glamorous as it appeared, and the neutrino experiments are starting to get new students.
I think just with regard to Eileen's question about when the new tau became became that priority. I think it was, and I don't think this has been mentioned yet at this conference, the first show experiment was done to study the hypothesis of nu E, nu mu oscillations as an explanation for the atmospheric neutrino problem. Because if you recall, at the time, the event rate seemed to be reasonably right. And so one explanation would be mu to E. But Show came up with no result. They saw no evidence for oscillations, which strongly implied that it was the tau. And so that experiment, which has not yet been discussed here, was critical in making that a motivation for the tau as the target.
The neutral current is an active neutrino. And if you see the neutral currents, you can derive that it is not a nu mu, and if it's not a nu e, it has to be a nu tau, because we measured at lab that there are 3 neutrinos. So that's a fairly, perfect agreement, a perfect argument, and it's never really been. I remember Super K making a sort of an argument that there was no stellar neutrino because they saw the neutral currents, and also already in 2000. But the argument was never pushed, what never followed to see how significant it was.
I'm going to weigh into the why do the experiment. I think it's incredibly satisfying for a donut to have produced a tau neutrino. Yes, we know that there are 3 neutrinos, but boy, wouldn't you be interested in a model question if they had done the experiment and they had no tau appearance. You knew there were 3, and yet. In the same sense, why would we do the IVB experiment to show that there were W's and Z's? We knew that there were neutral currents and charge currents, and we could measure the mass. I mean, I think it's a natural inclination. It was a successful thing for operant to have run and show tau appearance. And as for Gary's question of why did that happen, well, I think there was a natural inclination for CERN to want to do a long baseline experiment ever since Sakiki showed his famous cartoon of doing an experiment, and yet the cost of doing a near detector was so high that appearance was the only thing left that made sense when you have no near detector.
I would just comment that actually finding Z's and W's had additional advantages, because then you could study them and find their mass more accurately and their properties more accurately.
I think what you're saying is right, that it is beautiful to do those experiments and interesting. The point is what you derive from it in terms of what information do I know today that I didn't know before? And that is where there's a bit of an argument going on. I think that's really the point. Did I learn something new or did I not? Of course, if I had found something different result, maybe I would have learned something new. But if I found what I expected, did I learn something new anyway? Okay, and that's really the question.
Michel Cribier, Saclay. Just for the record, I want to remind also beam experiments which never happened, and there have been several. There have been a beam which were supposed to go through Jura, and François Vanucci, I'm surprised that he didn't mention. And also there was more recently all these beams which were supposed to go from CERN to Finland, to everywhere, in Italy and so in Sicily and so on. And okay, it doesn't happen, but I think it has been studied also.
Yeah, one comment I would make is the Icarus people kept thinking about what they could do. And there was a proposal at one point that I left out for sake of time to go off-axis from the Gran Sasso beam with a 5 kiloton liquid argon detector. Now, of course, this never got funded, and it would have been a beautiful experiment, except that it would have suffered from not having a near detector. But sort of none of these plans sort of worked out for Icarus.
Maybe one can just comment on Michel. Yeah, there are a lot of experiments that have been proposed. We know also high-intense source experiment that never will happen. So I mean, that's I think it's in our nature to propose more things than we can realize. So, Maury?
Maury Goodman, Argonne. So when the first beam was proposed to Sudan, there was also a proposal to send a beam to IMB. And then there came a third proposal to send the beam to a big lake in Arkansas that never got built called Project Grande. And when that came in, Taji Yamanuchi, who was the Fermilab program director, said, oh, we should just build an isotropic beam.
So we are running late, and I think I propose to close the discussion here.